logic in a weird way.
Hello, am I audible?
Yes, sir.
Okay, so let us start. Uh, should we wait for some time or let us start?
We can start, sir.
Okay, sir. Okay, is my screen visible now?
Yes, sir.
Okay. So, my name is Adnan Farooq Khan. I am PhD scholar at IIT Delhi, and I am here uh, the fifth week of our problem-solving session for the course Advanced Power Electronics and Control, which is being taught by Professor Avik Bhattacharya. Like on like every Tuesday, this is the problem-solving session from 7 to 9. Like for today's, like I'll be briefly going through what was taught in this week, like non-isolated DC-DC converters, and then what was taught is different types of choppers. Like we'll be briefly going through different types of choppers and isolated converters, and today like we'll be doing numericals on the topic that was taught in this week. Like today's numericals will be mostly numerical type, and I'll be guiding you through how to solve them, and which will subsequently help you in solving your assignments. like coming to the, like in the previous week we had discussed different non-isolated DC-DC converter topologies like buck converter, like buck DC-DC converter, by which we were able to step down the voltage from a certain level to the level which was needed as per our requirement. The other topology that was discussed last week was boost kind of a topology, where we had an input of some voltage and we wanted to, at the output we wanted to have a voltage that was higher than the input. And in those applications where we need a output voltage higher than the input, so our requirement is the voltage which is higher at the output than the input. At that time we used boost topology. And the other topology that was discussed in the last week was the buck boost kind of a topology. And in the buck boost topology, what we did, buck boost topology has the flexibility to have the both buck operation as well as the boost operation. If we wanted to have the voltage less than the our input voltage, we were able to achieve that, as well as we were able to boost our input voltage to higher level of voltages. These are the converters that were discussed in the previous week. Like continuing with that, like this week what was discussed is the choke converter. As you can see, this picture that is shown here is the circuit diagram of a choke converter, and it is being named after the inventor who discovered this topology, choke, and is named after that. And as you can see, if you like see this choke converter, as you can see, like we had seen in buck convert, if you can see on the input side of that we have an inductor and a switch. It is similar to what we had in the buck converter. Like we have in the buck converter we had an input, then inductor, then switch, then we had a diode, and then we had an output uh, like output capacitor. No, sorry, if you can see at the input, it is like a boost converter, like we saw in the boost converter, in the DC-DC converter, where we had an inductor, then the switch, and followed by it was a diode, and then we had a filter, output filter capacitor, and the load. And if you can see it here at the output, we have a structure that is similar to the buck converter, where we had a uh, an inductor at the output. So if you can see, like this choke converter is the combination of buck as well as the boost, buck as well as the boost topology. And this choke converter is able to have both buck as well as, similar to this buck boost converter, this choke converter has the ability to have the both buck as well as the boost, like we will be able to buck as well as the boost our voltage, our input voltage. But you can ask the question, like if we are having a buck boost converter, why do we need this choke converter? So like we are having different kind of topologies, like a buck converter, buck boost converter. If you can take a look at that topology and this topology, that you can see that here like if for some applications where we want like our current or our voltage to be smoother, or it won't be as stiff. Like for example, if we have a buck converter, uh, buck converter or boost converter, you can see like our input current is discontinuous for the buck converter, and if you can see here for this this choke converter, here we can see both the input as well as the output current is will be continuous, because we are having both inductance at the input as well as the output. Also, like we can have like a smaller ripple for the input current as well as the output current in this choke. converter. Let us say we are having an application where we want to have the smoother or this input current compared to the switch current as compared to the buck converter. There we can use this Chuk converter. So if you can see, the advantages of this Chuk converter is like we can have a continuous input and output currents. And here, like the disadvantage of this Chuk converter is that we are having like more number of filter components. Like if you could see, like our typical buck boost converter that had only one inductor and one capacitor, here you can see we are having two inductors and two capacitors. Like we are having four passive components compared to typical buck boost converter. So that is the disadvantage here, but the advantage that we are getting is like a continuous input and output current in the choke converter. So if we are having an application, like we can use this circuitry like this choke converter in an application where we are having applications in a way like where we want to have the smoother input current. There we can use this choke converter. Now after this, like choke converter, what was discussed is like different types of choppers were discussed. Like briefly I'll be telling you what a chopper is. Like a device. Let us say we are having a certain constant input voltage, and the output we want to have some variable voltage. Variable in the sense, let us say take a buck converter. If we are having a 100-volt input, we want, let us say, 10 volt, 20 volt, 50, 70, let a variable voltage at the output. Like a chopper is a device or a static device by which we will be able to have a variable voltage at the output. And coming to these choppers, like these choppers can be of different types. Like most probably like a five types I'll be discussing here, like what was discussed in the course that I'll be discussing here. And these types are on the basis of the current and the voltage conducting and blocking capability, voltage blocking capability and current conducting capability of this current conducting capability of this chopper device. Let us say we are having a voltage, we can have at the output, like we can have the positive voltage and negative voltage. Also we can have a positive current and negative current. Therefore considering this, we can have a four quadrant operations. Let us say if a converter is operating in the first quadrant, it is able to have the positive, it is able to have the positive current as well as the positive voltage at the output. And if our output is like a negative voltage but the current is positive, then we can say our converter is operating in the second quadrant. And similarly, if we are having a converter that is both negative voltage and the negative current, therefore our converter is operating in third quadrant. And if we are having a positive current but the negative voltage, then we can say our converter is operating in the fourth quadrant. So depending upon the direction of the depending upon the polarity of the voltage and the direction of the current, we can say that our converter is operating in a certain quadrant. And coming to the first chopper, like if you can see this chopper, it is known as a class A chopper. And if you can if you can take a look at this structure, it is typical buck type of a converter. Like here we are having a control device one and diode here, and at the output we are having a load, and load can be an RLE load, like where we have R as well as L and E. Let us say when this switch is turned on, we get this V in voltage at the output, and when this switch is turned off, like we get the zero voltage at the output. If our load is RLE type load, then since the current cannot be interrupted through the inductive load, that current will freewheel through this diode, this freewheeling diode. So this class A type of a chopper is the buck type of a circuitry which steps down our input voltage to some output voltage which is lower than the input. Here you can see, like as this is a buck type circuit, at the output we have a positive, we will be able to get the positive voltage only from the input, which is the lower than the input. And also the direction of the current is it will be able to have, if you can see this device is a SCR, it will be able to have only this direction of the current. If you're taking this direction as positive, so we can say that this kind of a converter is able to have positive voltage at the output on positive current at the output. So like, if you can see that we can say that this type of a chopper is quadrant 1 class A chopper, and it operates in the first quadrant because we have a positive voltage and the positive current here. The current cannot go negative here. Also, when this device is SCR or GTO, this should be a control device where we have control turn on as well as the turn off. That you know, if we are an SCR, we don't have any control over its turn off. So we can say here that this device is a GTO. So when this device is turned off, like the voltage, if it is an RLE load, the current will still continue to flow in this direction, but it will freewheel through this diode. So here you saw that we are able to have the positive voltage and the positive current. So we can see this converter, this chopper operates in the quadrant, first quadrant. So after that we'll see, you can see that there is another kind of a chopper which knows the class B chopper. And here if you can see the circuitry of it, as we see that our load is an RLE type load. When this voltage is positive, this diode will get reverse biased. This diode is reverse biased when V is V, because V is applied to the cathode, and here when we have an E, that will charge up. If we are having a RLE load here, then E will charge, this capacitor, this inductor, and this switch will be off, and this current will flow in this direction. So you can see here the voltage is positive at the output, but the direction of the current is negative to what it is shown here. So no, what here is like voltage is also negative. If you can see that this output voltage, we have shown the polarity here, but E, if you can see, it will be in this direction. So we'll be having a negative voltage that will be charging this inductor, and the current will flow through this device when this device is on, and the direction of the current will also be negative. And when this will turn off, and the polarity of the inductor will get reversed, and this diode will forward biased, and this current inductive, whatever the energy that is stored in the inductor, will be fed to the source. So this kind of a topology is this kind of a chopper is seen as the time of regeneration in the cars, where we need to have the negative energy power that we need to feed to the source. So here we can say this is the quadrant 2 second quadrant operation of this chopper. So it is there in the second quadrant because we have a negative voltage and negative current but positive voltage. As you can see, the voltage is positive, but it has only the negative current. So you can see that it is a quadrant second operation, as the current is negative, but voltage is still positive here. Moving towards the other class of chopper, we have a class C of chopper. And this chopper, if you can take a look at this chopper, if you take if you can see at my pointer, like this SCR and this diode, and if you see, and this circuitry will make it a class A chopper, like this SCR and this diode. And we were able to see that this with this chopper we had a positive voltage and a positive current. It was able to operate in the first quadrant. So with this SCR and this diode and this load connect across it, we have class A chopper. And if you can see this SCR and this diode, we can have we are having the class B type of a chopper, where we have a positive voltage at the output, but the current what we are having in this circuitry is negative. So here you can see, if you take this device and this device, this will conduct the negative current. So you can see, like in this kind of a chopper, we are able to have uh, two quadrant operation in quadrant 1 and quadrant 2. So in this type of chopper, at the output we are having a positive voltage only, but we saw here, when this through this device and this diode, we are able to have the we are able to conduct the positive current, and with this SCR and this diode will be able to conduct the negative current. So you saw, like at the output we have the positive voltage, but the current in this kind of a circuit can be both positive as well as negative. So this kind of a chopper is class C chopper, which operates in two quadrants, that is first and second quadrant. We are able to have the positive voltage across the load, but the current can be both positive as well as negative. So this kind of a chopper, we have a two quadrant operation. And now coming to the, like uh, class D chopper. Here, if you can see here, through the arrangement of the devices here, like SCR and this, uh, across the load in this kind of if we are having this kind of a circuitry, you can see, like we are having a RLE kind of a load, the load voltage can become positive or negative, but you can see this, the current direction is only in one direction. Like let us say, when the current is positive, it's able to conduct with through these devices, controllable devices here. And these switches are turned off, the current continues to conduct through these diodes, this diode and this diode. So here you can see, the direction of the current is the direction of current is the same, only in the positive direction. And if you can see, like let us say now we are having a negative current. If you see this SCR, this SCR is not able to conduct, will not be able to conduct this negative current. Neither will this diode. If our current direction is in a negative, let us say this direction, this won't be able to conduct this negative current, nor will be this diode. So the arrangement of this circuitry is in such a way, like we will be able to have the both polarities, like we can have both positive as well as the negative voltage at the load, but the current direction will only be positive. So you can see, then we can say this class of chopper can operate in first and the fourth quadrant, because we are having only the positive direction of the current, but the voltage can be either positive as well as negative. So this class of chopper is known as class D chopper. So up till now, like we saw, like we have a class A chopper, like which had the positive voltage and as well as positive current. It was able to have the quadrant 1 operation. Now we are then we saw the class B chopper, where we had the positive voltage at the output, but the current was negative. So we saw, like it is able to operate in the second quadrant. Then we saw like a combination of class A and class B chopper, where we had only the positive voltage at the output, but the current can be positive as well as the negative. So this class of chopper is like class C chopper, which operates in first and second quadrant. Then we saw, like now we saw arrange chopper, where the arrangement of devices was in such a way, like we were able to have only the positive current, but the voltage can be positive as well as negative. As such, like this class of chopper is known as class D chopper, which operates in the first and fourth quadrant. So here we saw, like in first, second and fourth, like we saw, like either we had a positive voltage and the current was bidirectional, then we had a first and second, or we saw like the current is unidirectional and we had the voltage with the positive as well as the negative polarity. Then we had a 1 and 4. And now let we want to see like if we can have a topology where both the polarities where we have both positive and the negative polarity for the voltage as well as positive and for positive and the negative current. We'll see that kind of a topology and that kind of a chopper. You could see like if you can see this kind of a topology uh, here, our voltage, we have an RLE kind of a load. Here the voltage can be both positive as well as the negative, and our current can be, see, if our current is positive and these and two devices on, it will flow through this, through these. Now let us say our current gets negative, so we can see our current can flow through this negative, this diode, through this source, and then through this diode. So we have a like a control device with an anti-parallel diode across it to conduct the negative current. Here we can also have for this like control device we can have an MOSFET or an IGBT. MOSFET has which have a like inbuilt in their device like this anti-parallel diode, which will be able to which is able to conduct this negative current. Similarly, like for this when this and this will be conducted, like we'll be able to have this negative current that will positive, when this and this divided, the positive like a negative current can be flow. If the positive is in this direction, then if this and this device are on, like it can flow through here, negative current, or positive can flow through this diode through anti-parallel. This will depend upon the switching that you are giving to these control devices. So with this kind of circuit, you can have like all the four quadrant operations. We can have operation in first quadrant, we can have operation in the second quadrant, we can have operation in the third quadrant, and similarly we can have operation in the fourth quadrant. So these are the different types of choppers that were discussed in this course. And after that, like some isolated converter topologies like flyback, forward, push pull kind of a topologies were discussed, which for which like we have some questions, like we'll be dealing with these questions, and at that time I'll be discussing about those isolations and all these converter topology. So we had a brief like review what was taught here, like a choke converter, which is the combination of a, like you can see a boost converter at the input and the buck at the output, like a combination of a buck and boost converter, and where we had an advantage of like continuous input as well as the output current. But the disadvantage here was like we had a large number of filter components like LC component, like here we had a 4 corresponding to 2 in conventional buck boost converter. Then we discussed about that choppers, like type A chopper operation which has operation in the first quadrant, type class B chopper which has operation in the second quadrant, class C chopper which has operation in first and second quadrant, class D chopper which has operation in the first and fourth quadrant, and class E chopper which has operation in all the 4 quadrants. So this was like the brief review, like recap what have been what was taught. Pranav, could you please like turn off your camera? So this was a brief overview what was being taught in this week. Now like we'll be going through some of the problems related to these concepts, what was being taught, up till now. So we'll start from this, like this is the first question is like DC-DC converter can be used as switching mode regulators. Like there are certain operations like you have to guess which of this is correct. Like first is to convert a non-regulated DC output voltage to regulated DC output voltage. Second is to convert a regulated DC output voltage to non-regulated DC output voltage. Option C is to convert high frequency AC input voltage to constant DC output voltage. Option D is all of the above. Like I think every one of you should be able to answer to this question. Like we have been discussing these DC-DC converters from past 2 weeks. So can anybody answer this question? Anyone? Am I audible now? So some one of you has talking about D, all of the above, and one of you has to convert non-regulated DC output voltage to regulated. So you can see like the basic idea behind this, like the correct option is to convert non-regulated DC output voltage to regulated DC output voltage. Now I'll make you understand like why this option is correct. Like the basic thing why we wanted to have this DC-DC converter is, let us say we are having some input voltage, let us say of 50 volts or 100 volts, but we required different output voltages at the output. Then we introduced some kind of a switching network by which we were able to switch we are able to switch in a certain way. So if we are having a buck kind of a topology, we are able to have like a voltage range which was lower than the input at the output. Or if we are having the switching network in such a way like a boost type of a topology, we are able to have the voltage at the output as per our need. So also besides this, for what we need this DC DC converters is, at the output we want to have certain voltage. Like let us say we are having, for the buck operation we need, let us say we are having an input of 100 volts, we need like a output of 70 volts at all moments, at all loading conditions. So we will be like these converters, by changing these duty ratio, we will be able to attain in this we'll be able to regulate this 70 volt at the output. And in a similar way, if we want to have a certain kind of a voltage, some constant voltage at the output, we want to regulate that voltage out the output, we will be switching our DC-DC converters accordingly so as to attain a regulated voltage at the output. And besides this, we can have different kind of levels of voltages as per our need due to these DC converters, rather than the stiff voltage that is available to us through like a DC source like a battery or something. So the option 1 is the correct option to this question. Uh, Everyone got now? Any confusion? If you have any confusion, you can ask the question, or if you have any questions, you can ask. So coming to the next question. So we have a second question. Like here what is being told, like we have a step down chopper, we have like fed from a 220 volt DC. This means like this chopper, we are having a step down chopper, that means a buck type of a chopper, with the input is like 220 volt. We are having a 220 volt at the input, and it's connected to an RL load, and it is given that the load is RL. We are having an R and L, with the R value is like 10 ohms and inductance value is 15 millihenry. Also what is given is chopper frequency is 1250, like 1250 hertz. What is this chopper frequency? Chopper frequency is the switching frequency of our device at which we are switching that. That is our chopper frequency. at frequency where we are turning on and turning off our devices. And what is also giving is like duty is cycle is 0.5. That means like our switch is being turned on for half a duration and is being turned off for other half duration. So what we have to calculate is what will be the maximum value of the ripple current. So we know like we have a bar kind of a chopper. At the load we have a RL kind of a load, and we want to have know what will be the maximum ripple of that IL, and certain options are given here like 2.85 ampere, 2.92 ampere. Like we'll solve this question and we'll reach to a certain answer and we can discuss that. So like as I had told, like this is a bug kind of a chopper, like class A chopper that we had seen earlier. Here the people like we have joined right now, for those I'll be telling like this is a class A chopper. Here you can see this is like a step down kind of a chopper. Here you can see we have a control device here, then diode, and we're having a RL load. So here what we saw is like at the output we have a positive voltage and the current is already only positive, and this kind of a chopper will operate in the first quadrant. So now let us see. If you can see here, what we were given is we were giving an input of 220 volts. So our input is 220 volts DC. So you can see when this device is turned on, when our control device is turned on, this voltage will come across this load. This like 220 volt DC will be implemented across the load R. So when this is implemented, like this will be our circuitry operation. When a positive voltage is like applied across this RL, like this IL will start to rise. Like we know VL is equal to L di by dt. When V is positive, like di by dt will be positive, so it will start to rise. And when, if you see, when this device is turned off, we have a zero voltage, like this will be short circuited, zero voltage across this, and the current, whatever the energy we had stored, it will start to like dissipate through this resistor. So we'll see if you can see this. So up to the point from 0 to dts, when this device is on, you can see this input voltage is connected to this load, and the uh, inductor will start to charge up, like the current in the inductor will start to rise up to this point dts when this switch is on. When this switch is on, and the charge of this will depend upon the time constant, that will depend upon this L by R ratio, that is tau, will give the time constant. If L by R ratio is too high, like our time constant is too high, that at that moment we can assume that since that time constant is very high compared to this switching time, we can assume that this rise in the current is linear. At that time we make that assumption. So here we'll see. So when this device is turned off at the DTS interval, so what happens is like there is no voltage across this, then this current will start to freely through this diode, and this will inductor will dissipate this energy through this resistance, and the value of this IL will start to decrease up till Ts. At that moment we will again turn on this device, and this voltage will be impressed across this load, so the current will begin to rise. So here you can see their current fluctuates between some peak value to some minimum value, like IA has some positive value and there is some minimum value here. and the if you can see the difference between this peak value to this minimum value is known as the ripple, or that is the difference between the peak value and the minimum value is known as the ripple in the quantity of that quantity. Here we are, what we are discussing about is the current, so here we can say the ripple current. So also, like, it is given what we have to see what will be the maximum value of the ripple current for these specifications. We have R, we have L is given, and duty ratio is given. So we saw, like, the ripple is the value of, like, from peak, positive peak, like a peak value to this minimum value. What is the difference between is the ripple, and here it is like uh, shown by delta IA. We represent the ripple. So now we, as you would have gone through the lecture that were taught, like, what was like, after solving this and after the mathematics of this type of topology, we can see that the ripple in this kind of a converter, like delta I, that is the maximum value minus minimum value, was given by this equation, like Vs by R. We have 1 minus e raised power d. D is the duty that is given already to us, that is 0.5. Here ts is the time period, overall time period, and we also is tau. I told you is L by R ratio. Like, everything is given to us here. If we are able to, now what we have to do, you just have to put these values in this equation and you will get the answer, like what is the maximum delta I will be getting for these parameters. So if you can see, like, first we'll be calculating the tau. What is given by, it is the time constant, it is L by R. So we, what is given to us, L is 15 millihenry and R is 10, and if you will divide these, we get like 1.5 millisecond will be the time constant. You got that? Everyone get it now? Any confusion or something, like, let me know, or if I'm going fast. Now what is needed is, like, tau we are able to like calculate, it is 1.5 milliseconds, and now we needed to calculate the ts. What is given to us is the frequency of, like, this switching, like this is the one cycle. When frequency is given to us, like, we can calculate the ts, which will be equal to the inverse of frequency 1 by fs, and here fs is 1250 hertz. 1250 hertz. Therefore, by after calculating, like, ts comes out to be equal to 800 microseconds. 800 microseconds. Now when we put these value of these, like tau, ts, and d, we know d is already given, like 0.5. So the ripple comes out, delta I ripple comes out to be around like 2.916 amperes. So, like, this was simple question on, only what you needed to know is this equation, the derivation of which is, like, discussed during the course, and what is known to us is, like, the ripple. If we are given, like, ts is given, tau is given, and d is given to us, we are able to calculate the ripple for these set of conditions. So here, for tau equal to 1.5 milliseconds and with the frequency of 1250 hertz, our ripple was around like 2.916 amperes. So the correct option is, like, B, 2.92 amps. Now coming to the third question. So the third question is, a step down chopper has a resistive load of 10 ohms. So here it is like similar to the previous question. Like this question is also on the step down chopper, but in the previous question what we had is like we had an RL load. Here only we are having R load. So what we got to know in the previous question, like due to this L, the rise in the current was slow. Like it was like if we are having tau very large, like this will be linear. But when we have only the R load here, the we see what will happen, and the input voltage is same, like 220 volts is same. So what is given is like when the converter switch remains on, it is given that when the converter switch is turned on, its voltage drop is 2 volts. That is like the voltage drop across the device is 2 volts. Then also what is given is like the chopping frequency is 1 kilohertz, like that is 1000 hertz. Like I told previously, like this chopping frequency is the frequency at which we are switching our device. So what is given here, if the duty cycle is 50%, then determine the RMS value of the fundamental component of the output harmonic voltage. So with this harmonics and all, you might think like this is some difficult question, but it is not. Like I'll walk through you the process what it is saying. What it is saying is like if the duty is cycle is 50%, that means here up till now we are getting the point, like R is given to us, load which is 10 ohm, input is given which is 220 volts, and the drop across the device is 2 volts. Chopping frequency is 1 kilohertz, and also it is given as duty cycle is 50%. That means 50% is D is equal to 0.5. Like for the 50% of the duration, the switch is turned on, and for the 50% of the duration, switch is turned off. We have to determine the RMS value of the fundamental component of the output harmonic voltage. Firstly, like we have to see what will be the output, what kind of a shape will be the output voltage of. So let us come to this. This is a step down chopper. When we are, if you can see, like this is a control device. When we turn on this device, this whole voltage is impressed across this. Since here is some drop, like with then this voltage will be equal to input voltage minus this drop. So it will be some constant DC voltage up to a DTS point, and when we turn off this device, the voltage across this will be 0. So you can see that the voltage will be some positive quantity up to a certain point, then it will be 0 for certain time, and then again when we are turning on this device, when we will turn on this device, it will again be positive. Just a minute. So you saw here in this step down of chopper, we have like a square wave kind of a voltage output waveform. This, if you can see, when from the time period 0 to DTS, that means when this device is on, we have a positive voltage across the load, like 0 to DTS we have a positive voltage, and when this device is turned off, then the voltage is 0. And it's also given like we have a duty ratio of 5. So the what will be the peak voltage when this device is turned on? So it will be like input voltage, which is Vs, minus Vch, that is like voltage drop across this chopper device. So the peak voltage be Vs minus Vch. Also it is given like our duty is 50%, like it is positive for 50% of the time and it is negative for the 50% of the time. So we can say, like, we can calculate as well, but intuitively we can also say that our average voltage will be at the half of this peak voltage, like because it is positive for certain for half a time and it is zero for half a time. So we can say like our average will be at the half of this square wave, like what will be the peak, our average will be at its half. So now we got to have, like, we got the shape of the output voltage, like it is a square wave. It is a square wave, but this square wave is like, if you can see, usually when we have a periodic wave like a sine wave, you see that it like it has a positive and some negative value. Here you can see like we are having a square wave, but it but it has a DC offset or a DC shift of Vs minus Vch by 2. So if we remove this, then you can see like we have a Vs minus Vch by 2. It can oscillate around like 0 line. Here it oscillates around like Vs minus Vch by 2 line. So now we got like our output voltage waveform is squarish kind of a waveform, and we have seen like now if we are able to apply the Fourier to this square wave, we can get our different harmonics. Like, you know, like square wave is comprised of different harmonics, all the harmonics like first, second, third, fourth, and all the harmonics. Now it will depend upon like if we are having a half wave symmetry, like there won't be any even harmonics. Then if you see other symmetry, like now as this square wave is made up of different harmonics, like one of the components, like major component, will be the fundamental. So this fundamental, as I told you, like if you can see this voltage square wave waveform, it is around it oscillates around this mean voltage of Vs minus Vch by 2. So you can see here like our fundamental will start from, our fundamental will be like, it will start from at 0, it will be at having a like Vs minus Vch by 2 value, and after completing one cycle it will be at the Ts, it will be at the same position. This is due to like we are having a DC offset of this Vs minus Vch. So this was our fundamental. So we know when we do the Fourier analysis, this square wave, and this is its mean, and you saw that this oscillates around this mean value. So we have seen that Fourier analysis, if we do the Fourier analysis of this square wave, we know that the fundamental of the square wave is given by this 4 by pi. We have like a peak of the VDC, we have peak of the square wave, that is like what is the peak of the VDC by 2 into sine omega t, that will be the fundamental component. But here you might ask what is, but here we have the peak value of Vs minus Ch. Why we have written like Vs minus Vch by 2? That is what I was like telling you before. If you can see, like this is a square wave around this mean value, like we have a mean of, it has a DC shift. If we remove this DC shift and shift this wave by Vs minus Vch by 2 downwards, then it will oscillate around, will have its square wave around like this 0 line. The peak value will be Vs minus Vch by 2. So in every, like whenever you see this thing, you will look like first look at if there is any DC offset or not in the wave. If there is, like then we have to, if we have to like calculate the fundamental first, like we have to like remove that DC offset or like calculate around that DC offset, then the peak value corresponding to this average value will be Vs minus Vch by 2. And also it is like sine omega t. Here this omega t like will have, like t will have this uh, value around this switching frequency, not the like a sine or like 50 or fundamental AC. Here we are dealing with high frequency, like it will have the value we have Ts, but we don't have to use here because we need to have the RMS value of it. So RMS value, we know it is the peak divided by root 2, whatever is the peak value, like this is the peak value, and if you divide it by root 2, like we will get in the RMS value. So our RMS value will be equal to V naught 1 4 by pi Vs minus Vch by 2 root 2. Now Vs is given to us, Vch is given to us, and if you put the values here, we can get the answer. Can anyone do the calculations and like put the values of like Vs minus Vch? I'll give you a minute or so. Can, like Vs is like 220 volt and Vch is 2. Now what will be the value of the RMS of the fundamental? Anyone? Anyone? So no one. If you can like put the values 4 by pi, Vs is 220 minus 2 and divided by 2 root 2, like this is the RMS value of the fundamental, and it will come around like 98.134 volts. That is the answer to this question. Everyone understood now? So the answer to this question is 98.13 volts. Now coming to the fourth question. Like we have the buck regulator has an input voltage of Vs is equal to 12 volt. Here it is, here it tells it is a buck regulator. First I read the question and I make you understand. A buck regulator has an input voltage of 12 volts. The required average output voltage is 5 volts, and at R like load resistance is given, that is 500 ohm, and the peak to peak output ripple voltage is 20 millivolt. What we want at output voltage ripple should be 20 millivolts only. So the output voltage should fluctuate between like we have an average value of 5 volts. Overall like ripple is like 20 millivolts. So we have an like peak value will be average plus delta V by 2, and minimum point will be average minus delta V by 2. That will be like our output voltage will fluctuate between 5 plus 10 millivolt and 5 minus 10 millivolts. Also what is given is a switching frequency is 20 kilohertz. Like our devices are being switched at 25 kilohertz. So also what is given, if the peak to peak ripple current of the inductor is limited to 0.8 amps. Now it is here we saw like ripple in the current is like peak value minus the minimum value, that is the ripple in the current. Here the condition is given like that needs to be equal to 0.8 amps. So our ripple is already defined, it is like 0.8 amps. What we have to determine is what is the filter inductance, what will be the filter inductance needed to have this amount of ripple. So it is given like a buck regulator. It is not a chopper where we have a switching device and a load. So when we are talking about the buck regulator, we have an inductor like a filter at the output, like which filters our output and the output voltage and the current. And we have an input voltage of 12 volts. At the output voltage we have some, we want 5 volt with some ripple of 20 millivolts. And also with, what is given in is 25 kilohertz frequency devices. We are operating at 25 kilohertz. Also it is given like the peak to peak ripple is limited to 8.8 amps. So we want to have this ripple only in the converter, and for that we need to calculate what will be the value of the inductor, so that the ripple in the current is equal to 0.8 amps. So many options are given, like some options like 145.83 millihenry, 150.59 microhenry, 145.83 microhenry, and 150.59 millihenry. So now we'll go towards solving this question. Like this is the buck converter, like this is the control device, and mostly this is uncontrolled diode. We can have a control error, that will be a synchronous one. Then this is an inductor, this is a capacitor, and this is the output voltage represented by VA. We have an input voltage Vs. So during the DTS operation, when 0 to DTS, when this switch is on, what is like across this inductor we have a Vs minus V out, like the inductor will start the current through the inductor will start to rise to some point, and when this is turned off, the voltage across this inductor is minus V out, and so the current through this inductor will start to fall some point. That will give us the ripple. So if you can see from 0 to DTS, if you can see 0 to DTS interval, take 0 to DTS interval, when this switch S1, like I'll show you the pointer. So when this switch is on, so the circuit becomes like this, this, and this. So across this inductor, what voltage is impressed is Vs minus, if we are having this plus minus polarity, we have a Vs minus Va by L, like, but the value of this is positive, so the current starts to rise from some minimum value, because this is in a steady state. We have taken the continuous conduction mode from some minimum value to some maximum value. It will start, current starts to rise. So and the slope of this current will be given by Vs minus Va divided by L, and this slope is positive, and as such current will start to rise up to this maximum point. So what happens like now when we turn off this device? When we turn off this device, when we are having a diode, current through the inductor cannot be interrupted, so this diode will start to conduct. You can see the voltage across this inductor will be negative. What will be impressed across it will be the minus V out, so the current will start to fall, as we have a negative slope that is given by minus Va by L. So you can say that current will start to fall, and current will continue to start fall until like TS portion when we turn on this device. And we know whatever it is stored in here, like the initial value should be same, like current will drop up to this point. So the difference between this peak value and the minimum value is the delta IL, that is the ripple, and we know, and it is given to us, it is equal to 0.8 amps, like this is given to us. Now what we need to see, what we have to calculate, the value, determine the value of the filter inductor to have this 0.8 amps. Now what we will do, we will take this interval 0 to DTS and apply the inductor equation for this interval. So we know like VL is equal to L di by dt, Till then it is fine. We know VL is equal to, if you can see VL, only this VL, for this VL will be equal to LDI by dt. So you can see for 0 to dts interval, the delta is IL is given to us. L needs to be calculated. We don't know L, but we know the input, we know the output, and is duty given, or we need to calculate the duty, and TS, like switching frequency, is given to us. So what will we do? L will be equal to, if we can, like L will take here, it will be equal to Vs minus Va, that these two are given to us, and we know for the buck converter D will be equal to V out by V in. So these two are also given to us. Also the Ts will be equal to 1 by Fs, that is also given to us, that is 1 kilohertz. Now each of this value we know, like this is 0.8, this is like 12, this is 5, this is given to us like 12, 5, and this is 1 by 1 kilohertz. Now you need to put on the values, and can you like solve this and tell me what is the answer to this question? Anyone? I'll give you like 1 2 minutes. Like these are the parameters, the equation I have. This is the equation. Anyone? I'll give you a minute or so. Everything is given here. Like you have to only put up the values. No one? So you know, like input is given to us is 12, output is 5, it is given to us. Delta IL is given to 0.8. Like input is given 5, our output is 5, input is 12, and also like the frequency is given. TS is called, we know, like 1 by Fs, like this frequency given. If we substitute this value, we'll come up with a value like 145.833 microhenry. Like this amount of inductance, if we put this amount of inductance and we operate uh, with the duty of like 5 by 12, having the 5 volt at the output and the 12 input, like we'll be having the ripple in the current that will be equal to 0.8 amps. Everyone got it? Any confusion? If there are any questions, like you can ask. So I think like therefore the options C is correct, like 145.83 microhenry. If you like take 145.83 millihenry, then the ripple will be reduced 10 times more, like 100 times more. Like this is milli, this is this, it will be 1000 times, like divided by this, it will be 0.0, it will be very minimal limit. So this was the fourth question. Now coming to the fifth question. So I think like here we'll take a break. Here we'll be taking the break for 5 minutes. We will be back by 8:15, 8:16, and we'll be solving other questions. Now let us continue with this question. Now here we are having question number 5. Question number 5 is a buck regulator has an input voltage of 12 volts. The required average output voltage is 5 volts. At R is like load resistance is given like 500 ohms, and it's also given like peak to peak output voltage ripple is 20 millivolts. Like it is similar to the previous question, and the switching frequency is 25 kilohertz. Also it is given if the peak to peak ripple current of the inductor is limited to 0.8 amps, determine the critical value of the filter inductance and the critical value of the filter capacitance. Like this is similar to the previous question. Now here what we need to see is we need to have this, we need to calculate the critical value of the filter inductance, the critical value of the filter capacitance for the current and voltage. Now we're going through what is this critical value. Now we know that we have a buck converter, like we have this switching device, and then we have here the diode, and when this switch conductance, we have a positive voltage slope, and like previously we solved this, we are able to have this. If you solve those equations of the buck converter, you will getting that ripple is given by these equations. And if we like have two equations for the two intervals for 0 to dts and 1 minus dts for the capacitor current through the capacitor, we get this equation delta vc will become vs d 1 minus d 8 l c f square. Like this is we taught in your course. You can see these equations there in the for this like week where this buck converter is being taught. Now what is given, like we have given conditions are like delta il is like 0.8 amps and delta vc is given. So these two things are defined to us. When we have seen, if we put these values here, like input, we know d will be equal for buck converter, it will be v out upon v in. That we also know, this is 5 divided by 12, vs is this, and 1 minus d. So delta il is like 0.8 into 25 kilohertz is the frequency, and what we get the value is like 145.83 microhenry, which is similar to the previous question. And for C, to have this ripple of like 20 millivolts in the voltage, if we put this here delta V and L, we are able to calculate from the above equation. We can see like C comes out to be equal to 200 microfarad. Like this is like the CCM condition. These are not the critical conditions. This is like the CCM conditions, and to meet these conditions of like delta L equal to 0.8 amps and delta VC of 20 millivolts, we need to have this at the switching frequency of 25 kilohertz. We need to have L value around 145 microhenry and capacitor value of 200 microfarad. Now we talk about the critical conditions. What is like this critical condition? What do you mean by critical condition? Here in CCM, if you can see, like previously we saw, like in the CCM, our current will rise from some minimum value to some maximum value and come back to this minimum value. Now if we let our ripple to increase, we will be decreasing our inductance, so our ripple will increase, and now our current inductor current will start at some lower point and will go to some higher peak point, and then it will come to back here. And similarly, when we are further going to like reduce, like a point will come where the current will start from the zero, go to some peak point and come back to zero. This condition is known as the critical or boundary condition, because after this what will happen, like if we further reduce like this inductance, like current will go to some peak value and it will reach to a zero before this TS interval, and after that, if you can see in the buck circuitry, the current will become negative and this diode won't be able to conduct that negative current, so the current will be zero in that interval, for that interval. And if our converter operates in under those conditions, then we say that our converter operates in DCM mode, that is discontinuous conduction mode. Here we can see that our conduction is interrupted, like the current is getting zero for some amount of time. We don't want that. So if you can see here, like for this boundary condition, current starts from the zero, goes to some peak value and comes to like zero value. Now this is the boundary condition. So if you can see, like this is a triangular current, and you can see that the average of this triangle is somewhat around like the half of this triangle, the average. And if you can see, like if this is the mean and if this is the half of this, we can say the ripple will be twice of this, the average current. Like this will be the average and this peak point will be twice of that. So if you can see, we can say like for the boundary condition, delta I will be equal to twice of the average current. We know that I out will be equal to V out by R. Also we know that V out is equal to D into V in. So we will be able to have our delta L. If you substitute this value, now this was our first one equations. Now we'll have another equations, like if we like in the previous question, like we had applied, like we know delta I is equal to L di by dt. For this current equation, we'll come up with this. To calculate the L, we will have this equations. For here, if you can see this equation we had talked earlier. So here for this critical condition, what we have, we know that delta L is equal to 2 dVs by R. So if we substitute this value here, so what we get, LC will be equal to 1 minus d R by 2 Fs. So what will be the value of LC for this critical condition? We know that LC, like D is known to us like 5 by 200, R is also known that it is given like 500, and Fs is also equal to like 25k. So if we put these values here, so we will be getting around L around to be 5.8 millihenry. So to have the critical condition, what we need to have in the previous circuitry, we need to put, if we have an inductor value of around 5.83 millihenry, we will be getting this critical or boundary condition. Similarly, like here I have for this, like this is the previous of that. For this delta V at the critical, like it will be equal to twice the output voltage on the similar grounds. Like if you can see, you can go through, and if we put that in this C equation, it comes out around to this equation. And if we substitute the value of D and L, what actually we had got earlier, to have this critical condition for this C, then you can put that value here and we will be getting the critical condition for C equal to 0.4 microfarad. It is simple, like we have to see. So For the critical value of the filter inductance and the filter capacitance will be equal to 5.83 millihenry and 0.4 microfarad. That is the answer to this fifth question. If there will be any doubts, and you can ask. Now moving on to the question number 6. Now it is given a boost regulator has an input voltage of 5 volts. The average output voltage is 15 volt and the average load current is 0.5 amps. The switching frequency is 25 kilohertz. If L is 150 microhenry and C is 220 microfarad, determine the ripple voltage of the filter capacitor. What we need, like these are the parameters. We have a boost here, it is giving, we have a boost converter, input is 5, output is 15, and average load current is also given. So what we need to, for this certain like L and C that are given, we need to determine what will be the ripple voltage of the filter capacitor. So we have this like a boost converter topology. L, when first, like for DTS this portion will be on, and when for DTS to TS, like this device will be on, and for 0 to DTS L will be having a Vs voltage, like it will be storing the energy, and when this will be on, it will be Vs minus V out. For that interval 0 to DTS, the current through the capacitor will be minus I out. You can see by this equation. So for the to calculate the voltage, we need to, like we'll be seeing the current through the capacitor. As I told, like for 0 to DTS, like this switch will be on, so inductor will be charging and the current through the capacitor will be negative of the load current. You can see that will be minus IA, will be through the capacitor. Now when at the DTS, when this switch is turned off and this switches will be turned on, so like the voltage across inductor will be Vs minus this V out, and you can see the current through the capacitor will be whatever current will be flowing through the inductor IL. If you apply this KCL equation here, the current through the capacitor will be IL minus IA, that is this IL minus IA. And if you can see, like IC will be having the shape of this inductor current, and the ripple portion of this inductor current will flow through the capacitor, and the average ripple portion of the IL will flow through the capacitor, and the average will flow through the load. So this will be like IC will be 0 like minus IA in 0 to DTS, and it will be IL minus IA having this shape like a negative slope, because current will be decreasing in that interval. So IL will be IL minus IA. So now we know, like current through the capacitor will be IC is equal to C dV by dt. So IC in this 0 to DTS interval we know is IA, and if you can substitute there in DTS, will be divided, will be getting the delta VC by C. Also we know, like D for the boost converter is 1 minus will be equal to V in minus V out. So that is given to us, like that is 5 and 15. So that is 1 by 3. If 1 minus 1 by 3 will be equal to 2 by 3, that will be D will come out to be 2 by 3. So after that, if we substitute these value in this, like we know IA is given, like average of the output current is given 0.5 amps. D is around to be equal to like 2.2 by 3, that is calculated already. And after that, like C is like given to 20 micro, and TS will be equal to we can substitute like TS1 by Fs, that is 25 kilohertz. So if we calculate that, this delta V ripple will come around to be 60.606 millivolts. That's the answer to this question, like 60.61 millivolts is the answer to the question number 6. It is like these questions are quite simple. Like you have to see in what is being asked in the question, and where can we solve this equation, and what are the required parameters that need to be found out, and what is given. Coming to the question number 7. Now what is here it tells the buck boost regulator has an input voltage of 12 volts. The duty cycle is 0.25. The switching frequency is 25 kilohertz. The inductance is given is 150 micro, and the capacitance is 220 microfarad. The average load current is 1.25 amps. Determine the peak to peak ripple current of this delta I. Like it is similar to the previous question. Like previously we had to find out the ripple in the voltage output volt. Here we have to find a ripple in the current. So what we'll do, like we'll solve some inductor equation for a certain interval, and we'll be getting that. We know that for the buck boost topology, for 0 to DTS, this switch will be on and this inductor will be charged. Like for the voltage across this inductor will be input voltage for the DTS interval. For the output voltage, like this voltage plus this voltage will be equal to, like, minus this voltage will be impressed across this inductor in the output. So you can see, oh sorry, for this, when this will be on, when this device will be on, this device will be off. So during the turn off, this voltage will be impressed across this inductor. As we know, the output of this buck boost converter is inverted, so the negative voltage will be impressed across the inductor. As such, the inductor current will start to decrease. So from 0 to DTS, current will start to rise up to DTS position, because this device will be turned on and the current through the inductor voltage is positive, di by dt will be positive, and current will start to rise up to a peak point. And after, when this switch is turned off, this source is disconnected, and when this will be on, usually here it's a diode which gets forward biased, and this voltage will be impressed across this inductor. And since this, we saw in the previous week, like this voltage is inverted, like then this negative voltage will be impressed across this inductor, and it will start, the current will start to decrease to a minimum point. And we saw earlier, like this peak value to minimum value, we called it ripple. That is delta IL is the ripple current. So this ripple current is given to us, like it is, no, we have to calculate this ripple current, but the average is like given to us. So we can apply this inductor equation for the 0 to DTS interval. Like we know LDL is equal to LDI by dt, and for this DTS interval, VL is Vs. This Vs is known to us. Now we need to calculate D. TS is known to us, that is a switching frequency, and L is given. So D is also given, like 0.25. So you have to do nothing, like just put up these values here. V is this, D is this, L is 150 micro, and L is given to be 150 micro, and TS we can represent it by 1 by Fs, 25 kilohertz. This delta L will come around to be equal to 0.8 amps. This is the answer to this question. So the answer to this question number 7 is part A, 0.8 amps. Now we will move forward to question number 8. The input voltage of a choke converter is 12 volts. It is given like a choke converter. Now that we had discussed at the beginning, the input voltage of a choke converter is 12 volts, and here also what is given, the duty cycle is 0.25, and the switching frequency is 25 kilohertz is the switching frequency at which the choke converter is being operated. So as we know, like we have two inductances and two capacitances for this choke converter. So the filter L2, that's on the load side, is 150 microhenry, and the filter capacitor is C2 is 220 microfarad. And the energy transfer capacitance, that is like on the boost side, on the front end side, is C1 is 200 microfarad, and inductance L1 is 180 microfarad. The average load current is given 1.25 amps. What we have to determine is determine the average output voltage. Like this question is, if you take a look at this question, there is a lot of information that is given here which is not needed for this question. If you know the basic equation for the output and input and output relation between this, for this choke converter, you will be able to solve this question. So we need a, if you can see, this is a choke converter, and this is will be the L1. We saw that this is a combination of buck boost converter, and you can see this will be L1, this will be C1, this is L2, this is C2, this is C2 here. And if you can, if you could recollect what has been taught during the course, the, like for the buck converter, like we know V out is equal to V out by V in is equal to D, or V out is equal to D into V in. In on the similar cases, like we know, like if you solve like apply this voltage balance and charge balance equation across these capacitors, these two capacitors and inductors, you will get to solve, you will get an equation like the relation between the input and the output, that is V is equal to minus D 1 minus D into V in. Also, like this is because like we have taken the polarity in this way, and since this polarity is inverted in the choke converter as well, we can have D into 1 minus D into Vs. So if we like put the values here, we know like D is equal to 0.25, that is given. Vs is also given, like 12 volts. So the output voltage will come around to be minus 4 volts. That is the answer to this question, like minus 4. Now question number 9 is a good question, like good question in a sense. We will this is on this flyback converter. So what is given for this steady state analysis purpose, the operational condition and power stage parameters of flyback converter are, what I have given here, like input voltage is given, like Vs, that is given, that is 24 volt, and the magnetizing inductance is 160 microhenry. Also N2 by N1 is like given 0.5, like this is the ratio output turns to the input. The filter capacitance is given, like C is given, it is 400 microfarad. Also the load resistance is given, that is 2.5 ohm. Also this switching time period TS is given, that is 20 microseconds. And also what is being given is the duty ratio for which the switch is operated is 0.4. So what is to be determined is determine the average magnetizing current of the converter. So I haven't discussed about the flyback. First I'll be discussing about this flyback converter, and we'll see what is this magnetizing inductance. So N1 is the number of turns, N2 is the primary turns, N2 is the number of turns in the secondary. So this is the like circuit of this flyback converter, where we are having a coupled inductor, and the primary of in the primary of this inductor we have a device, controllable device here, which is usually anything like GTO, MOSFET, IGBT, anything. And on the secondary side we have a second device, which is usually a diode. So you can see here, this is like more or less not a transformer. This is mainly a coupled inductor which stores the energy in one half and transfers the energy in the other half. In the transformer, the transfer of energy is continuously throughout the operation, but here, like for one interval the energy is getting stored, the for the other interval the energy is getting delivered. So like we will getting the equivalent transformer model of this, and it is represented in this way, like the primary of is which stores the energy is represented by this magnetizing inductance parallel to this primary, and the secondary is shown here. So we'll see, like we'll be having like the two intervals, like when we turn on this device, and for the other half when we turn off this device, and this device will be turned on. So if you can take a look, just a minute, I'll like lower this diagram a bit. Now first we'll take 0 to DTS interval. For this interval, what is done is like this switch is closed, like this switch is turned on, and you can see this switch is if you can see, when this switch is turned on, then this dot will have this positive voltage, and this dot will have we're having a positive voltage in this sense. And we'll be having at this output, like due to this dot point we'll be having a positive here, negative. So since we are having a diode here in this direction, it will be like forward, it will be like reverse biased, this diode, so this will be open. So when this is open, there is no secondary current, there is be no current in the secondary, as such there will be no current in the primary, only therefore there will be only one current, that will be this magnetizing current in this interval. So what will happen when this, for this interval 0 to DTS, the current will flow through this magnetizing inductor and it will start to charge. Like when positive voltage is applied across it, we are having a positive di by dt. So current will rise from some zero value to some peak value. When it reaches this peak value, like at the moment when this device is turned off, so what will happen? We know that the current through the inductor cannot be interrupted instantaneously, so it will try to continue flow in this direction. So when it continues to flow in this direction, so it will flow here out of the dot. So in this on the primary side it will flow out of the dot, so on the secondary it should flow into the dot. So the direction of the current will be here in this direction, which will forward bias the diode. So when this diode gets forward biased, the voltage across the secondary will be V out, and because of this, like the voltage on the due to the this transformer action, the voltage across this primary will be V out by N, since we have a turns ratio of 1:N. So the voltage that will be across this LM will be V out by N. So but with this opposite polarity, so current will start to decrease. So it will reach up to this point and current will then decrease to a minimum point, up to the point when this switch is again turned on. This was about this IM. Now we will see IC. So for 0 to DTS interval, the current like this device was off, so the current through the capacitor was the negative of the output current. So IC will be equal to minus I A. And for when this device is turned off and this device is turned on, like this capacitor will be equal to like the current that will flow through the primary, and due to this some current will flow through the secondary, that will be equal to Im by n, and the current through the capacitor will be equal to Im by n minus Ia. If you can see these equations, it are similar to the buck boost topology. So what we need to have here, what we have to calculate is average of this magnetizing current. So we'll apply this equation, inductor equation, for this. Just a minute. It increases to up to a point, then decreases. So we can apply our equation in a certain interval from 0 to dts. So uh, if we take like a charge balance, for this charge balance, like we'll apply this charge balance for this equations, we need to calculate the Im value. We have like for d this 0 to dts, we have a d into minus Ia, like this, plus 1 minus d interval, we will be having Im by n minus Ia will be equal to 0. And if you solve this equation, Im will come out to be In n times Ia divided by 1 minus d. Just a minute. So also, like we know, like this is for the flyback converter, output and input have a relation similar to this buck boost topology, like we have n d 1 minus d vs. So if we put the value, n is given to us, like d is also given, d is given 0.4. So if we put the 0.4 and vs is also given, we have the output equal to like 8 volts. And also, like we know, the average output current will be equal to like whatever is the output voltage divided by resistance. Like we know the output voltage out will be equal to 8 volt divided by 2.5, that will come out to be 3.2 amps. So now we got to know the Ia is now known to us. Now to calculate the Im, we needed to know the Ia. So when Ia is known to us, we can put the value of this Ia in this equation, and Im will come out to be around 2.667 amps. This is the answer to this question. 2.67 amps. Now coming to the last question. A chopper may be thought as a inverter with the DC input, DC equivalent of an AC transformer, C diode rectifier, or DC equivalent of an induction generator. I think you should be able to answer this question. Can anyone guess what is the answer to this question? Anyone? One of you has like answered it, like, oh, as like the we were started to like discuss these DC converters. One is like inverter with a DC input. So the basic idea here is like, why do we needed this DC kind of choppers or certain things? Like if we are having an AC, let us first talk about the AC. We had a device, namely the transformer, which was able to change our voltage levels from one voltage level to other. Like we had some voltage level, if we want to step it down, we use a step down transformer, or we want to step up, we use a step up transformer. But we didn't have any kind of a DC transformer there which could like change the voltage levels of this DC's input. Like we have a step DC, we want to change this DC voltage. So then we like introduce some kind of a switch, like we were like switching the inverter for certain amount of time, like we saw a switching circuit, and we were able to have a regulated or a controlled voltage at the output. Okay, I'll complete this question and I'll come to be like Shaikh, I'll come to be like this flyback once again. So by like changing this switching scheme, like we were able to have different levels of voltages at the output. So if you can see in that terminology, we can say like a chopper might be thought of as DC equivalent of an AC transformer. See, if you want to have a different voltage levels at in kind of an AC, we simply put up the transformer. But what we do for the DC, we use a chopping circuit. Like if we want to have, we can have a buck type, boost type, or any other type. So you can, in terms of that analogy, we can have like DC. This is an equivalent to an AC transformer, but this chopper can be considered as a DC equivalent of an AC transformer. So the option B is correct. So this was for today, like the questions that needs to be discussed up till now. So like Shaikh is asking me to like explain like once again the flyback converter. So here you can see this is the circuit diagram of this flyback converter. What we have instead, this is kind of an isolated DC-DC converter. It's an isolated buck boost type of a converter. Just a minute. So yeah, so this is the topology for this flyback converter. This is an isolated. Here we have introduced some isolation. If you can see like this portion, if you can are able to like see, this is like a buck boost topology. If you remember, we had an input like this inductor at the input, and then we had some switch, then diode, which was able to like do the buck boost type operation. Here what is it like? This is an isolated buck boost topology. Here we cannot say like this is a transformer, this is like usually a coupled inductor, because in transformer we transfer the energy like flux changes, and we have an induced due to the primary, then we have an induced EMF at the output, and there is a continuous transfer of energy. But here we can see like we are having a like two devices. This device is a I'll show with the pointer. This device will be the control device, and this will usually be diode with the cathode towards the load. So this is the transformer equivalent, how we represent this flyback converter with an LM here. Up till now this is clear, Shaikh? Up to this point it is clear? Like you can comment yes or no in the chat. Yes, up to this. Now we'll see like different operating stages, like modes, like we saw in this buck converter or boost converter. Let us see first. We will see like 0 to DTS interval. 0 to DTS interval. We know like in 0 to DTS we turn on the switch. When we turn on this switch, are you getting this? When we turn on this switch, this LM is connect across this, so this Vs voltage will be across some LM. Since this is parallel to this primary, this voltage will be here, come across this primary. But when we this voltage will be dot will be this side positive, so here it will be this side positive, this side negative. When we are having a diode with the cathode here, we are having a positive voltage from here, negative voltage here. This diode is reverse biased, and so that this will be an open. So when this is open, no current can flow through the secondary side because the circuit is open on the secondary. So when no current is in the secondary, there can be no current in the primary, because like due to transformer action, if there is a current in the primary, some current needs to be flow on the secondary side to balance it. So this was this. So only current that will flow in through the primary is through the LM. ILM, since this is the voltage that is getting impressed across the LM, it is some positive voltage. We know V L is equal to L di by dt. So when V is positive, di by dt is positive, so current will start to rise. This is the IM current. Also, if you can see on the secondary side, this side is like not connected to this circuitry at this moment. The current through this capacitor will be the negative, the current that will flow through the load. So IC will be equal to minus IA, that is negative here, in this 0 to TTS interval. Up to this point, is it clear? This mode of operation, it is clear? Yes. So we can move forward. Like this is 0 to DTS. Similarly, we can see DTS to TS interval. What happens in this mode? Like this device is now turned off. When this device is turned off, we know the current through this inductor cannot change instantaneously. So this current needs to flow in the same direction. So it will flow. The only path it is through this. It will flow. It cannot flow through here because this is not connected. It will flow through here. So if you can see the current direction in this way, current will flow out of the dot here. So if you know the dot convention, so if the current is flowed out of the dot, current will flow into the dot on the secondary side. So when the current will flow this way, it will like forward bias, this current will forward bias this diode and it will start conducting. You got it? When this will start conducting, so this voltage will come across the secondary. So secondary voltage will be equal to this output voltage VA. If you can see, these points are connected here. When this is here, due to the transformer action, like the voltage, this will be like negative, this will be positive. So this dot will be negative, this will be positive, and what it will be impressed, it will be V out by N due to the transformer action. Got it? When this is V out by N, like since this is the negative voltage that is impressed across this L, current will slowly start to decrease through this inductance. IM will start to decrease. But what we need to see what is happening due to this capacitor current. So before this interval, the capacitor current was the negative of IA. Now you can see this current, there is some current that is flowing through here, that is IM. So due to this IM, the secondary current will be equal to IM by N. This current will be IM by N due to the transformer action. So if you can apply KCL here at this node, the current through the capacitor will be equal to IM by N minus I out, that is IA. That will be the average current that will flow through this capacitor. So the waveform will be something like this through the capacitive current. It is clear up to this now? Clear? Yes. So when it is clear, like these are your modes of operation. All you need to do is like apply this charge balance and here this voltage balance equations. You can see through the notes and you will come up with these equations. Like for DTS it's minus I by, sorry, it is minus IA by here 1 minus D interval, current is IM by N, because like in the capacitor whatever the energy is stored in certain interval, it needs to like give back that energy in other interval. That is meant by this equation, like charge capacitor charge should be balanced, and if you solve this you will come up with this equation. And similarly you can do for here as well. For the IM you will come up with this equation, like the buck boost type of topology. That is, you can go through the notes what has been taught to the circuitry I made you explain, and you can come up with this equation. You can come up with that. Is it clear now, the operation of this flyback converter? Shaik, it is clear? Okay, it's fine. Any other question? I think it is 9. I think like we can close it here. If there are no, any other questions, I think this was it for today. Thank you for joining. Thank you. Pranav, you have some question? You can ask. Pranav, you have some question? You can type the question or you can ask the question. It's nothing. Thank you. Thank you. Okay, this is for today. Okay, I think we shall close here. Good night, everyone.